Hi there, welcome back. Arrays are an imperative programming language resource that provide a fundamental way for structuring and accessing information. They are indexed collections of values that have a given name. In this lecture, we will define arrays and use them in two examples. Arrays are total functions over a domain that is an interval of integers with 0 as a lower bound. As an example, you have the array R with elements A, B, C, and D. The indexes are 0, 1, 2, and 3. Therefore, R of 0 equals A, R of 1 equals B, R of 2 equals C, and R of 3 equals D. So we have the function R, which represents the array as the function that maps 0 to A, 1 to B, 2 to C, and 3 to D. The values in the arrays are accessed using their respective indexes. They can be read and changed as conventional variables. For example, if we assign the value E to the third element of R, we have the array R changed by removing the D and putting the letter E instead. So we have the final function R, which maps 3 to the new element E. You can also assign the whole array at once. In this example here, we assign to R the Cartesian product between the set that ranges from 0 to 3 with the set F. So we have the final array R with all elements equals to F. Multiple assignments, however, are not allowed. We must use relational overriding to make these assignments. For example, if we want to change the first element and the second element of the array R, we cannot assign R0 and R1 the values E and F. This is simply not allowed. We can, however, make this assignment here. We assign to R the relational overriding of R using the set 0 mapped to E and 1 mapped to F. And as a consequence, we change in the array the values A and B for E and F respectively. As an example, we will present a machine that registers the number of guests in each room of a hotel. In this hotel, we have a set of small rooms that have the maximum capacity of 4 guests. All other rooms have a capacity of 6 guests. The operations we have in the machine are: we can check in a given room with a given number of guests. This number, of course, must respect the room's capacity. We can check out a given room. We can inform the number of guests of a given room. We can inform the number of empty rooms. And we can swap the number of guests of 2 given rooms. For example, let's suppose we start the hotel with small rooms being room 1, 2, and 3. And let us now suppose that we check in 4 guests in room 1, we check in 2 guests in room 2, we check in 6 guests in room 4, and we check in 5 guests in room 5. Now, if we ask how many vacancies we have, the answer will be 1, because we only have the room 3 available. However, if we ask how many guests we have the sum of the guests of room 1, 2, 4, and 5, giving us the answer 17. Let us now suppose that we swap the number of guests of room 1 with room 2, and that we check out room 5. Now, if we ask how many vacancies we have, the answer will be 2, because we have rooms 3 and 5 available. And if we ask how many guests we have, the answer will be the sum of rooms 1, 2, and 4, giving us the answer 12. Let us now see this example running in Atelier B and Pro B. Let us now present the machine hotel. The machine hotel has two constants, small and size, in the set room. The size is a natural number that defines the cardinality of the set room. So card room equals size. And small is the set of small rooms. So it's a subset of room. We have only one variable, numbers, which is defined as a total function from room to the range 0 to 6. However, the relational image of these function numbers on the set of small rooms is a subset of 0 and 4 that restricts the number of guests in the small rooms to be 4 at most. We initialize this number function mapping all the rooms to 0. So we assign to numbers the Cartesian product between room, the set of rooms, and the set containing only the number 0. And that gives us the function that maps all the rooms to 0. Now we have 6 operations: check-in, check-out, room query, vacancies, total guests, and swap. The operation check-in receives a room and a number between 1 and 6, and the numbers of the given room should be equal to 0. That means that the room, you can only check in on empty rooms. And finally, if the room that's given is a small room, then the number of guests must be less or equal to 4. If all those conditions are satisfied, we can check in the rooms assigning NN to numbers of RR. The next operation is the checkout, which receives a room and simply assigns 0 to numbers of RR. Next, we have the room query, which receives also a room and gives the output the number of guests of that room. So it assigns to the output NN the value of numbers of RR. The operation vacancies simply gives us the number of rooms that are empty. So we restrict the function numbers, we make a range restriction on the set containing 0, and that gives us all the mappings, all the relations between the rooms and the number of guests, but only for those who are mapped to 0. And if we get the cardinality of that set, we have the number of rooms that are empty. That means the number of rooms that are mapped to 0. The next operation, total guests, uses a special function, sigma, which is the summation of all of the quantity of guests of all rooms. So we make the sigma of ZZ such that ZZ belongs to room, and we sum all the numbers of ZZ. So that's the way we use to return the sum of the total sum of the guests of the hotel. Finally, we have the swap, which also receives 2 rooms, RR and SS. However, both rooms must have the same size. So if RR is small, then SS is small, or if SS is small, then RR is small. So actually what we have is that RR is small if and only if SS is small. And that guarantees that the RR and SS have the same size. So what we do is we swap the number of guests of both rooms. So we override the function numbers using the relational overriding with the mapping of RR to the number of guests of SS and maps SS to the number of guests of RR. And that completes the definition of our hotel. Let us now open this machine in Pro-B. We have exactly the same machine, and we can, for example, set up the constants to have 5 rooms, so we have the cardinality 5, and we set the set of small rooms to be 1, 2, and 3, exactly as we had in our animation. Now let's check in 4 guests. Let's initialize the machine. Let's check in 4 guests in room 1. Let's check in 2 guests in room 2. Let's check in 6 guests in room 4. And let's check in 5 guests in room 5. Now you can see here in the left that room 1 has 4 guests, room 2 has 2 guests, room 3 is empty, room 4 has 6 guests, and room 5 has 5 guests. Now if we ask the vacancies of this hotel, we get 1 as output, meaning that we have only 1 room empty, which, as we know, is the room 3 here. Now if we ask how many guests we have using the operation total guests, we have 70 as output, which corresponds to the sum of all numbers of guests of all the rooms. Now let us swap room 1 with room 2. Notice that before swapping, room 1 has 4 guests and room 2 has 2 guests. Now if we apply the swap, we have now a different mapping. Room 1 mapped to 2 and room 2 mapped to 4. Let us now also check out room 5. Now we see that the vacancies operation is returning 2 vacancies, and the number of guests is now, calling the operation total guests, is now 12. And that completes the animation of our abstract machine hotel, exactly as we did in the animation previously in this lecture. Arrays may also store values of other types. For example, our hotel may store the name of the clients in the rooms. In this example, the operations would be check in a given room with a given guest name, check out a given room, inform the name of a guest of a given room, inform if a given name is in the hotel, and swap the guests of 2 given rooms. Let's start the hotel with 5 rooms again. Again, rooms 1 to room 5. Now, let's check in the guest Marcel in room 1. And let's check in the guest Gabriela in room 2. And finally, let us check in the guest Thierry in room 3. If we ask which guest is in room 1, the answer will be Marcel. And now let's swap room 1 with room 2, and let's check out room 3. Again, if we ask which guest is in room 1, the answer now will be Gabriela. So let us now see the machine, the abstract machine that stores the name of the guests for each room. We call that machine hotel guests. The machine hotel guests has 3 sets: the set of rooms, called room, the set of names, called name, and the set report that is defined here in this machine and contains 2 elements: present and not present. This machine has 2 constants: empty and size. Size, as for the previous machine in this lecture, is also a natural number greater than 0, and also represents the size of the set of rooms. And empty for us is a special name. So empty is a name that will be used to represent the name of the guests of empty rooms. So we have here a variable called guests that is defined as a total function from rooms to name. As we said, the special constant empty will be the name used to empty rooms. So guests is initialized with the mapping of rooms to empty. So we have the Cartesian product of the set of rooms to the set containing only empty, and that results in a mapping of all the rooms to the name empty. Now we have 5 operations: the guest check-in, the guest check-out, the guest query, the present query, and the guest swap. The guest check-in receives a room and a name. But the name has to be a valid guest name, so it cannot be empty. And what it does is that it assigns to the guest of RR the name N. So it maps the room RR to the name NN. The guest checkout receives a room and assigns to guest of RR the name empty. The guest query returns the name of the guest that is in the given room. So it receives a room and returns, assigning to NN the value of guests of RR. The present query returns present if the name of the guest that is given as an argument is in the hotel. So it receives a name NN, which cannot be the name empty. And if NN belongs to the range of guests, that means that the name is in the hotel. So we return present, assigning present to RR. Otherwise, we assign not present to RR. Finally, we have the guest swap, which swap the name of the guest of two rooms. So it receives two rooms, RR and SS, and overrides the mapping guests with the mapping RR to guests of SS and SS to guests of RR. So that actually makes the swap of the name of the two given rooms. So let us now see how this machine can be animated in Probe. So we now open the hotel guest, and here we are using the trick of naming the elements of the set. So here we have 4 guests: Marcel, Thierry, Michael, and Gabriela. So let us now initialize our machine, and now we start the hotel with 5 rooms. Notice that initially all the rooms are empty. Now let's check in Marcel to room 1. Let's check in Gabriela to room 2. And now let's suppose we want to check in Thierry to room 3. Notice that Thierry is not here to room 3. This option is not shown here in the list of enabled operations. You can change that in the number of operations available here, of options for each operation available here. You can change that in the configurations of Probe, or you can also simply invoke an operation. Let's say guest check-in, and give the parameters here, the arguments. So we have that the room is room 3, and that the guest is Thierry. Now if we execute that, it successfully executes the operation, and as you can see here in the left, we have Thierry in room 3. Now if I ask which guest is in room 1, the answer will be Marcel. If I ask which guest is in room 2, and the answer is Gabriela, and so on. Now let's swap the guests of room 1 and room 2. Notice that here we have room 1 mapped to Marcel, room 2 mapped to Gabriela, and if we make the swap, this mapping is changed, and now room 1 is mapped to Gabriela and room 2 is mapped to Marcel. And of course, if I ask which guest is in room 1, using guest query of room 1, the answer will be, as expected, Gabriela. And that completes this lecture. See you in the next one. Bye.